Okay, hello. Mm. Mm. Hi, it's been a while since I last live stream on this platform. Sorry for that. I've been really busy these days because of the change of the environment. Now hopefully I'll be able to do a live stream more constantly from now on. Now, so this is Junichiro Horikawa, and this is the live stream for Houdini tutorial. And I have been doing this weekly, but recently it's been really inconsistent. It's not really constant anymore, so can't say this is weekly anymore, but hopefully I'll be able to continue. Now, today, the topic for today is to implement so-called Centroidal Voronoi Tessellations, and I'm going to create a weighted version of Centroidal Voronoi Tessellation today. So the Centroidal Voronoi Tessellation is to create the center of the Voronoi to be in the minimum energy for the Voronoi as much as possible, meaning make the centroid of the Voronoi to where you can create really smooth hexagonal shape. And there's a lot of ways to implement this computationally. One of the easiest ways is to use so-called Lloyd Algorithm. So that's what I'm going to use today. But there are many other ways, like using k-means clustering, quasi-Newton method, like BFGS. Now, if you just want to get the result like these in Houdini, then the easiest way is to just use the scatter node with the relaxation option on. By using it, you can just create a bunch of points on specific surface. With this relaxation iterations on, you'll have somewhat evenly distributed points, which would be a similar result to what you get out of SCVT, so-called Centroidal Voronoi Tessellations. Something like this. If you use the Lloyd algorithm, what you get is kind of an animated result. I'll show you. And you could also set a weight to the centroid of the Voronoi. I'll explain the algorithm later, but the result you get is something looking like this. It doesn't really have to have a weight, but if the weight is all equal for all the grid surface, then you get the similar result as the scatter point. But you can also set a weight attribute to the grid as this. Maybe used as a color attribute and use it for the weight for the distribution. Now you could still use this together with the scatter point to create a similar result, and it's much faster. So if you just want to get the result, then you can just always use scatter node, and that's that's it. But it's just if you would want to implement the algorithm by yourself using CVT. Could be fun because of some computational method that I'm going to explain, some simple method. And one of the benefit of this centroidal Voronoi tessellation is that it could also be used for a volume. It could use the volume density to distribute points inside the volume evenly. Now it probably could, you could probably do that using a scatter node as well, but I'll just show you how you could, if you want to implement it by yourself, then it might be useful making it as a prototype in Houdini and bring it to some other software, like using C++ or other softwares like Rhino, Grasshopper. Okay, so the topic is pretty simple. Just implementing the traditional CVT, a weighted version of CVT. Okay, so let's do this. Hello everybody, thanks for coming and thanks for all the comments. Okay, sorry I have been missing these days. I'll check the Patreon message as well. Thanks. And thank you, Jason, for super chat. Appreciate that. Have you ever tried Python over Vertex? Yeah, I've been using Python in Houdini a lot as well, especially when it comes to IOs, like file IOs. That's when I really need to use Python, or maybe some small machine learning stuff as well. Okay, so that's that. Let's try to implement this from scratch, just the sake of education. Okay, so first let me explain how the Lloyd algorithm works with my dirty sketch. So first you create a initial Voronoi setup using a bunch of points. This might look something like this. Okay. Oh, the method for the Lloyd algorithm is really simple. You just pick every polygon, the Voronoi polygon, and calculate its centroid, which probably is at the different places for the initial center point for the Voronoi. Well, how do I call it? The cell point. The centroid of the polygon is different from the cell point of the Voronoi. Okay, so you first calculate the centroid of Voronoi, and using a iterated method, something like solver, to move this point over to the centroid of the polygon and recreate the Voronoi using this new centroid position, which will create a bit more distributed result compared to the last one. And if you continue doing this, same thing again and again, recalculating the centroid and move the cell point to the new polygon centroid, in the end you'll get pretty cleanly distributed hexagonal like shape like this. So that's the Lloyd algorithm, and you can add an attribute. You can use the attribute for the underlying geometry or the surface to kind of control the way the point moves toward the centroid, meaning by setting the centroid, the goal points, which in this case a centroid of the polygon, to somewhere else by using some kind of a weight underneath. You can create an interesting effect using the same Lloyd algorithm, something like gradual polygonal distribution and that. So for the attributes under the surface, on the surface underlying this Voronoi, could be anything, could be like color attributes, or could also be volume, anything. So that's one of the reasons you could use it for a three-dimensional geometry. You could use for the 3D surface, same method for 3D surface. You just need to calculate the combinatorial centroid of each surface by dividing it to a bunch of triangles, and calculate the centroid for each triangles and take the average. You'll get the centroid of the polygon. So that's how you can calculate the centroid for the 3D surface, which you could also just use the measure node in Houdini. And you could also use this for a volume as well. The volume centroid could also be calculated pretty easily by dividing this into a tetrahedron. Or you could also just use a measure node in Houdini. And in this case, the application of this Centroidal Voronoi Tessellation could be used for something like FEM, finite element analysis, for engineering most of the time, to make the geometry clean and nice. Now, which could probably be done, everything be done using just one scatter node, but why not do it by yourself to study what's going on here? Okay, so let's try. Hello Hags, thank you for the super chat. Hello. So that's that. Let's try to create the setup. First, I'm gonna create a geometry node. I'm gonna start with the flat surface, then try out with the 3D surface, then probably do the volume as well. The volume part, I'll just gonna create the simple Centroidal Voronoi instead of just weighted version, because you need to calculate the centroid for the 3D shape by yourself. But if I found it easy, then I might just try. But let's see. Let's start with the flat surface. Just gonna go with the grid. Have you tried Material X and Calma? Yeah, a little bit. I've tried using my Windows PC. Right now I'm using Mac, so it's not really decent. But on Windows, I tried it and found it really nice. Okay, so let's start by creating initial points for the Voronoi. Let's make this non-relaxed so that we can see the changes clearly. Okay, and just gonna go right into the solver, connect. So what I want to change is the point position, the cell point position for the Voronoi to make it distributed nicely. So just gonna the one that I want to change, it's gonna go to the first input, and I am going to connect the grid, which is going to be the guide geometry, to create the Voronoi to go into the second input. Right, let me just save this. Okay, weighted. Oops. Okay, I shouldn't have had backslash. Okay, now, so I'm going inside the solver, and first thing I would like to do is to create the initial Voronoi with this points. So the grid comes to the first input of the Voronoi, and points comes to the second input. Now, one thing I really wanted to try out before going into the live is to make this process as efficient as possible, because if you have like tons of points, 10,000 points, 100,000 points, this will become vastly slow. So it's not really suitable for a large number of points for this method. So the way I could optimize is to somehow replace this with some other options. What you just need is to get is the centroid of the Voronoi cells. You don't really need the edge informations, but I tried using more like a shader like process. It was fast, but the result is not as precise as the vector geometry like this one. So probably this is better if you need the precision. If you don't really need the precision, just need the rough result, then you could use the shader like process, making a bunch of points as a sampling points to calculate kind of a rough centroid information of each Voronoi cell. If you're interested, I could also show you that, but the result is not that precise. Okay, so once I get the Voronoi structure, what you want to do is to calculate the centroid of each polygon, which is different from the cell point. This is the cell point, but the centroid of the polygon is different position. So the easiest way in Houdini to calculate that is just to use the measure node, calculate the centroid, which will give you a primitive attribute called centroid. Now and what I would like to do is to change the position of each point to this centroid point position. Okay, so to do that, I could just use the primitive wrangle. There's two ways you can do it. One is to change the original point position with the centroid of this Voronoi, which could be the fastest way, but there's a chance that the Voronoi cell might decrease because some point goes outside. I mean, in this case it might not happen, but in those cases the number of the cell might differ from this one and this point number. So the safest way is to just get the centroid information from each primitive and just remove the original primitive. So add the new point from the centroid attribute, then remove the current primitive. Okay. Now if you compare this point to the cell point, you see there's a little shift going on for each cell, right? And make this go to the output, and this is just it to iteratively move the point to the centroid of newly created Voronoi. Now if you see the result, if you play it gradually, okay, I'm seeing the cache here. You can see that gradually it's distributing the points nicely, evenly, like that. And with this number of points, it's pretty fast. Okay. If you increase the number of points, then the cost of Voronoi calculation might increase, might gonna be slow. For example, if you say like 100,000 points, this is gonna be slow, because each time you have to calculate the Voronoi geometry first in order to get the centroid in this way. Okay, so it's pretty slow. Yeah. I'll just stop. So if you just want to get the result, then you can just turn on the relax iteration here. Make the iteration number higher to have a result faster. Maybe you need more iterations for this number of points. You still see some gradual gradation here. Well, that's that. Maybe 10,000 might work. Oops. So you can see gradually it's the point position is changing. And if you spend much time, then it's gonna become really evenly distributed points. But as you can see, it's not that fast. Yeah, even though I'm doing this as efficient as possible in this case, but this one is always taking a lot of time to calculate. And if you look into it, actually this piece, each piece node is the most time consuming node. Okay, so maybe I'll later show you the rough calculation way, how you can estimate the centroid of the Voronoi roughly, but makes it more time efficient. But for now, let's go with the precise version. Now I'm gonna make this go back to 1000 for the testing, and now I'm going to try to implement the weighted version of the Centroidal Voronoi Tessellations, meaning I'm going to place some attributes to the original grid. Then based on those attributes on the surface, we'd like to try to change the centroid of the polygon, shift the centroid position to the weight based on the weight on the surface. So in those cases, you cannot really use the measure node, so you have to calculate the centroid by yourself. in order to use the attributes. So next thing I'm gonna do is to replace this measure node with a point wrangle just to calculate the centroid or primitive wrangle. Okay. Calculating the centroid for the polygon is pretty easy, pretty straightforward. If you have a cell like this, first you divide the polygon into a bunch of triangles like this. Then calculate the centroid of each triangles, which is the average of each point. Do the same for all the triangles. And after you get all the centroid for the triangles, calculate the average of these three, or every triangle centroid. And that's the centroid of the polygon. Easy as that. And that's the result is the same for the 3D surface as well. You just need to divide the polygon into a bunch of triangles, and which is called as combinatorial way for the discrete geometry. Right, so let's do that. So let's try to get all the vertices from the primitive. Alright, then loop through all the vertices. Now, what I want to make sure is check if the first vertex number of this primitive and the last vertex number of this primitive is if the same or not. Let's check. So starting point BTS 0, end point BTS, just to make sure if I need to loop back to the starting position or not. Okay, let's check. So starting point and the end point is different. So that means, yeah, I need to loop back into the first point inside this iteration. Okay, meaning what I'm gonna do now is to start looping with the number of points. In this case, I have 1, 2, 3, 4, 5 points, starting with 0. And I'm gonna fix one of the points, something like 0. Then loop from 1, start the loop from 1. Then in the iteration I equals to 1 or 0, get the first point, which is this one, and get the second point, which is this one. Then connect these points together. In the next loop iteration, you start from 2, then get the next point 3, connect with the fixed 0 points, give the triangles, do the same for the last one, start from 3, 4, connect with fixed 1 and 3. So if you have 5 points, then the number of iteration in this case is 3. So 5 minus 2, meaning the number of points minus 2 is the number of loop you should do. Alright. So let's do that. So in this case, this is the number of loop you need. And well, the other way is to just use the divide node and get the triangles for each polygon and calculate the centroid for each one using measure node. But let's make it a bit flexible way, shall we? So where was it? Where were we? So int vt1, the first vertex. Now I'm gonna fix one of the vertex. I'm gonna call this vt0, which is this one. And you can't just use the vertex number as it is. You need to get the point position in order to calculate the centroid. I mean the centroid of the triangle. So convert it into a point number. The reason why I'm using prim vertices instead of prim points is that it preserves the order of the point for the polygon. It goes, I forgot which way, but it goes clockwise order or counterclockwise order for the point number. If this is 0, then it might go 0, 1, 2, 3, 4, 5. If you use prim vertices, but if you use prim points, it doesn't go like clockwise or counterclockwise. It just goes random. Like this could be 0, this could be 4, this could be 3, and so on. So it's not really suitable for this kind of usage. Okay. Get the point position. Right. Now, inside the loop, you first get the pt1 starting from I plus 1. I mean, maybe I should yeah, I plus 1. Then pt2 is vts I plus 2. Okay, should do it. So if I is equal to 0, you get 1 and 2. If I is equal to 1, then you get 2 and 3, and so on. Okay, do the same for all the vertices. Convert it into a point number. Get the point position. For each point. Alright. Now, now you get 3-point positions. You can now calculate the centroid of the triangles by just calculating the average. So try centroid is position 0 plus position 1 plus position 2 divided by 3. Alright, now I'm going to add this triangle centroid to the some variable for the vector outside the final centroid, starting with 0, 0, 0. I'm gonna add it, increment the final centroid with the number of triangle centroid, and then in the end I'm going to make it average by dividing it by the number of loop. In this case, this is the number of loop, so like this, and you should be able to get the centroid for each primitive. Now that seems like a lot of calculation, but this will become useful when you want to implement other like method inside it in order to modify how you move the centroid position. So let's check if this is correct by comparing with the measure node result. So this is the one from the Vex. The first result is something like this: negative 1.76 minus 0.32. If I check this one, okay, it's a look different. It looks different. Maybe I'm doing something wrong here. Yeah, it looks different. Okay, maybe I'm doing something wrong. Let me check the one that I implemented previously. See what I did wrong. Let's see. Oh, wait a minute. Maybe I'm counting wrong. If I have 1, 2, 3, 4, 5 points, okay, then yeah, the number of loop is correct, I think. And so call goes from 0. I have vertex point number. Okay. What did I do wrong? Oh yeah, I forgot to... I might need to also... okay, I need the area information as well. Forgot. So in order to get the centroid correctly, I also need to use this area of each triangle as the weight. So for each triangles you have different area, like A1, A2, A3, right? So after you get the centroid of the triangles, you need to add all these points together with this area as a weight. So if this is C1, C2, and C3, what you need to do is to C1 multiplied by A1 plus C2 multiplied by A2 plus C3 multiplied by A3 divide by A1 plus A2 plus A3, right? And that this is the correct method to calculate the centroid. Sorry for that. Okay. So I have a question. Why don't you use prim points to get the prim points in the first line? The reason is because prim points doesn't give you an ordered point number for the primitive. Sometimes it gives you like 0, 3, 2, 1, 4, something like that. The prim vertices always give you the ordered point number, clockwise or counterclockwise, I forgot which, but it will always increment by 1 in terms of the number of vertex number. So that's more convenient in this case, because you need to go from the point to the next point to the next point to the next point in order to get the triangle information. If you just need the random point position for each loop iterations, then prim points is fine. But in this case, maybe not. So, where was I? Yeah, I need to calculate the area as well. So let's do that. To calculate the area for a triangle, let's give another mathematical equations. So if this is P1, P2, P3, and if you want to get the area of these triangles, what you could do is to first create the two vectors which creates these triangles from P1 to P2, from P1 to P3. Okay. And if you calculate the cross product of this vector, you get this perpendicular value by P1, P2 to P1, P3. Let's call this V. And the interesting fact is that the length of this vector value is equal to the area of this equirectangle shape. So if you divide it by 2, you get the area of triangles. So the length of cross product divided by 2 is the area of the triangle. Okay. So that's that. Let's calculate it. First create a vector value direction from 0 to 1. Oops. Where was I? Position 1 minus position 0. Position 2 minus position 0. Okay. Then the area of the triangle is cross product of this two direction, get the lengths, multiply by 0.5. Okay, so this should be the triangle area. Now let's have another variable outside the loop called total area. And increment this total area with each triangle area. Then for the centroid of the triangles, I'm going to multiply area here. Okay, and finally, when I calculate the centroid, I am going to divide by, instead of divide by the number of loop, I'm going to divide it by the total area. Total. Okay, so this should do it, and let's see the result. So going back to the centroid, so it looks like these, minus 1.70, minus 0.249, and yeah, if you go to the measure node, you get exactly the same result. Cool. Alright, so that was it. Now, now you get the centroid of the polygon. It's time you use the weighted information underneath to modify this direction or the centroid somewhere around here. Okay, so I'm gonna call this CVT, and let's create some attribute informations on top of this surface. Okay, so gonna use the remesh node to remesh the original grid, define the resolution of this mesh, how you want to apply the attributes. Let's make this 0.1. Okay, now attribute name could be anything, but it might be easier to see using the color attributes. So let's try to use that. I'm gonna try with the simple color distribution, something like noise, using noise function based on the point position multiplied by the scale of the position. Okay, and I'm using F instead of V because I just need singular value. This will create the monochrome gradation. Okay, maybe this is too big. And distribution is in between 0.3 to 0.7, I think, which might be okay. So I'll just use it as it is. This might be too small. Let's go with the setup. It's a bit hard to see, but you can see, you gradually see there's a color difference in areas. And I'm going to use these color differences as a weighted value to move the centroid. Probably move the centroid position based on those weight value. So I don't know, if it's close to white, if it's close to 1, you might want to make the points more attracted to those direction. If it's dark, maybe you want to go repelled from those direction. So meaning you could calculate the gradient on specific points in which way the point should go based on the weighted value. Okay, so let's do that. I'm gonna connect this to the third input. And try to use it when you calculate the Centroidal Voronoi Tessellation, shall we? So, guess there are many ways to use this. There are no specific ways to use this. Maybe there is a paper for it, but I haven't searched for it. I'm just gonna do my way. So the way that I'm gonna do is to recalculate the centroid of each triangles somewhere around here by using the weight underneath. Okay, so for each triangles, I'm gonna explain in sketch. Each triangles underneath, you are going to have a bunch of it's really hard to see. Underneath, you're going to have a bunch of points or a mesh which has this weight information. And this might have a weight equal to 1, this might have a weight equal to 0, this might have a weight equal to 0.5, and so on. Okay, so when we were calculating the centroid for this triangles, we were getting the point position of the triangle, P1, P2, P3. and multiply by the area. Okay, so that was how I was calculating the centroid. No, actually, I was dividing it by 3 and multiply by a. Okay, now instead of using 3, I could use the weight get at each point. So for example, if I'm looking at P1, the weight might be equal to 0.5. So I could use 0.5 plus, if it's P3, and if it's equal to 1, then 1. I mean, P3 is here. And if it's P2, if it's equal to 0, then 0 here. Now do the same multiplication above as well. So P1 multiplied by 0.5, P2 multiplied by 0, P3 multiplied by 1, P2 will go on. So the final result for the weighted centroid of this triangle will be P1 multiplied by 0.5 plus P3 multiplied by A. Okay. This way you could shift the original centroid to by using weighted information. We'll be getting close to the more higher weight position. If everything is equal to 1, or if everything is equal to the same value, then you get the same result as before, just dividing 3 with P1, P2, P3. But if one of the value is higher or lower, then the centroid is gonna be shifted. Okay, so that's how it's gonna work. Let's see how you could implement that. So for what I want to do is to sample the weight for each position 0, position 1, and position 2 to use it for the weight of this triangle centroid instead of just adding everything equally and divided by 3. Try to modify this using those weight. So for the position 0, it's fixed, so I can sample the value here. Let's call this W, and the sampling method is, there are several sampling methods to get the value from the other input. Probably in this case the easiest way is to use the UV sample. So let's do that. Float W equal UV sample 1. What you want to get is the CD attribute using point as a sampling attribute, using position 0 to sample. Okay, so I'm gonna call this W0. Do the same for all the points. For position 1, position 2, we just replace the value here. Gonna make sure if I'm having the CD. Yeah, so I'm trying to get the CD value for each triangle point position by using UV sample. You're gonna get the linearly interpolated value. Okay, then now that I have W0, 1, 2, it's time you could multiply each weight to the position, just like you did to the area, and divide it by the total number of weight. So W0 plus W1 plus W2. One thing you're gonna make sure is that if you have all the weight to be equal to 0, then you're gonna get the error, because the value is gonna become infinite. So you're gonna make sure there are no 0 weight in this implementation. That's one thing you have to be careful. Those values should not be equal to 0. Okay. Now let's see what happens. Going outside the loop and check how it's gonna move. Reset the viewport, play it. Okay, it's a bit hard to see if things are changing or not. Let me check if I'm doing this right. Think so. At least it's moving, so let's try to make a bit more contrast for this noise function. Let me go back to the... Maybe the contrast is a bit too low here. Let's make a high contrast. What I'm gonna do is to... I don't know. Probably using some kind of a sigmoid function, or maybe just using ramp parameter to control the contrast, just like you do in using the level curve in Photoshop. Okay. Okay, this will give you more contrast, I guess. Right. Okay, let's see. So, go back, play it. Now you start to see more weighted distribution than before. Yeah. Places where it's dark have less points. Places where it's bright have more points, more distributed points. But as I said, if you just want to get this kind of result, you can just use scatter node and use a density attribute. Instead of using density, just use CD. And wait, I don't have right here. And you get similar result. Much faster. I don't know how what's the algorithm under for this one, but it's pretty close to what we get here if you increase the iteration. The good thing is faster. Yeah, so it's always good to have a fast result. So for the production, I guess you should always choose this one if you just need this result like this. If you somehow you want to get the animation like these one, then maybe this makes sense to use this way. Okay. And that's pretty much it. The other way. I'll show you how some other way to create the weight, something like based on the photograph or something, maybe. but in order to get the result out of the photographs, you need a bunch more points, so gonna have to wait a little bit more to get the result. Well, let's try. I'm gonna use image from Pexels, which is the free copyright images. Just use some, I don't know, simple image, maybe a high contrast image. Fruit. Maybe this is good. Maybe this is good. Alright. Yeah, I'll try this one. Yellow might be taken as white. Well. I mean, anything is fine. Okay, I'll break this one. Okay, I'm gonna copy this to the desktop. Try to get that using attribute map for this mesh. Load the texture, which is on the desktop. Okay, I don't see it. WebP. I'm not sure if I can use. Okay, there you go. The aspect ratio is a bit squashed, but this is just a try, so I'm just gonna go with this. It should look from here, or maybe I could increase the size for the height a little bit. Yeah, like that. Okay, now what I need to do is to convert this color information to the weight, in this case a contrast information, I guess. So I could make this float for the CD, which will give you a monochrome result, but you still get vector results, so you wanna just convert it into a float value here. So how do I do that? I am just going to maybe use this one, or just copy this. Just get the CD information from the second input. Falsely convert the vector into a float. This doesn't look elegant, but anyway. And maybe I would like to have the level curve as well, to give more contrast. Alright, and as I said, I gotta have to make sure that there are no zero value for the weight. Now maybe I can do the clamp to make sure that I don't get zero. Maybe for the one as well. Just in case. Okay, now connect this to the third input solver. See what happens. Maybe in this case I need more points in order to see the effect. So let's go with 5,000 points. So yeah, I am getting something here. And if you look the result together with the final Voronoi fracture. You'll see how the Voronoi is being distributed like this. Yeah, interesting. Okay, so this is the Centroidal Voronoi Tessellation. Well, I'll use RGB to HSV to convert color, get the saturations to drive the density of points. Sounds good. Let's try to do that. RGB2. Oh yeah, you mean the function. Color. RGB2HSV, and you can convert the CT here, get the saturation. Saturation is the second value, I guess. So and the result is maybe I'm missing something, or should I get the value here? Maybe, yeah, the value, this one here, which will be kind of a brightness, I guess. So the result might be pretty similar because the grid looks pretty similar. Anyway, that's CVT, the weighted CVT, and let's now see how you can use this for three-dimensional surface. More surface like I don't know, pig head or something like that. If you want to do the similar things in pig head, again, you can also use scatter points always, and it's much easier. But if you want to try to get the animation like I showed you here for the 3D surface, you could do that too. Now, things that I need to be careful of is when I create the Voronoi out of this pig head using the initial point, in this case here. Several things that I need to be careful of. It's a bit hard to see the edges, but you are getting the trimmed edge here. And if you just want to place the points on top of the surface, then you don't really need the interior surface. So check off this one, which will be faster as well. Let's make it 1000 as well to make it faster. Okay, and what we need to do now is to calculate the centroid for each cell, split it by the Voronoi, which already has a bunch of edges here. So you need to consider about these triangles as well. So you need to know which face belongs to which cells, right? So you need to have those information stored on each primitive points. So I'm gonna promote these information like piece and cell PT. Cell PT is the original point position for the Voronoi, which is this one. Yeah. In this case, I should switch the initial point position to the big head. So I'm gonna give switch node so that I can switch between either flat surface or 3D surface. Just connect it right here. So I'm gonna make the system more versatile, which can be used for the 3D surface or 2D surface at the same time. Alright, so what was he? So this is where I'm calculating the weight. This is testing. And this should go here. Let's go here and switch to the one so that I can test with the pig head. Okay, now if I click this Voronoi and double click one of the primitive, I get the total primitive for each cell. And what I need to do is to calculate the centroid of this geometry by dividing every primitive into triangles, just like I did previously, and recalculate the centroid, and based on the weight I have here and create a new centroidal information. So to do that, I needed this information here, and if I have that, if you go to the primitive, you get cell PT, which is the point number of this one, which primitive belongs to which point, and the piece is pretty much the same information, I guess. Okay, that's alright. Well, if I have these information, then I can group the primitive based on those attributes. So that's what I would like to do here. Okay, so that's that. Let's go inside the solver and update the CVT calculation to make it more versatile. First thing first, I'm going to disable the interior surface, because you're not dealing with the volume here, you're just dealing with the surface here. Okay, now next thing I would like to do is to promote the attributes like piece and cell PT. I don't know which one's better to use. Maybe cell PT, or I don't know, maybe piece. In this case, it's not gonna change the value. If the point just goes away, if the point is not being used for the cell, then the number, there's gonna be a gap between piece and cell PT. Piece always starts from 0, so maybe this is better. Okay, so I'm gonna use that, and what I should do here, this implementation can be used if the Voronoi cell is just one piece. But if you have multiple pieces to create one cell, then you need to update the implementation a little bit. So let's see how I could do that. Well, maybe I could calculate for each cell here first using primitive wrangle, then add all the informations later per cells with additional wrangle here, then calculate the final centroid for each cell. Maybe that's better because you don't need to make a loop inside here. Which gonna be a little bit faster, I guess. So let's do that way. So for each primitive you have additional piece attributes, so we're gonna use that somewhere. But for now, what I would like to do is, I don't want to calculate the final centroid at this point yet. I wanna bring the total centroid here before dividing by the total area to the primitive attribute. Then do the same for every cell piece. Then finally add all the triangle based centroid, triangle based area, and divide by the final total triangle area. So I'm gonna comment this out, then I'm gonna name this piece-based final piece-based centroid, or triangle centroid, piece-based area. Which is equal to the final centroid and total area. Okay, let's see what happens. So I have the piece area here, which is the area for each pieces, and the piece triangle centroid, which is the centroid information for each pieces. Now, now what you want to do is to add all these values together for each cells and divide it by total area. Okay, this has to be vector value. Okay, so I'm gonna use the attribute promote to add those attributes per piece per cell. So the value is in primitive, and you are going to store that, and where should I store that? Maybe to the same primitive. And the original name is, what was it? Piece. Try centroid. Was it? Piece tricent. Yeah. Piece tricent, and what I want to get is the sum. And change the name to total tricentroid. Okay, I'm getting error here. No promotion specified. Source and destination classes identical. And I wanna change this to piece here, so that the sum will be calculated per piece. If this has the same piece number, then all the values in this piece will be summed up. Let's check. So the total triangle centroid. So these share the same piece number, I think. Yep, piece 0. And it's having the same value, which is the result of the mass addition. Okay, do the same for a total area. Piece area, total area, total piece area. Yeah. Okay, let's check. The total area is like this. Okay. Now I could now calculate the centroid somewhere before. Somewhere around here. How do I call this? Weighted average. Now the final result should be the piece triangle centroid divided by the total area, piece total area. So what's the name? Piece tricen, total tricen, total area. Okay, so the centroid is total centroid divided by total area. Okay, now you could add the points to those places, but the problem is wait, you are getting duplicated points on each primitive cells, because if the piece has 4 polygons, then you're gonna have 4 points created with this method. So that's not good. So instead I should just move the original point position, which is this one, to the centroid position. Right. In that case maybe I should use cell PT instead of piece. That make more sense. Okay, so instead of piece, I'm going to use a cell PT here to attribute, to promote. And after this, I'm going to use the point wrangle for the original piece centroidal point. And I think I have connected the wrong piece here. Not connecting the points here. Where did the point go? This one. This has to go to the first input. Yup. Okay. Okay. So I have points, I have Voronoi. Yep, looks correct. Then what I would like to do is to move the original point to the newly calculated centroid position by referring to this centroid that I have here, by picking up the corresponding cell PT value here. Right? Now each cell has different number of cell PT or pieces, so one of the way you could find the corresponding value is to get the first attribute which shares the same attribute called cell PT, and each primitive which shares the same cell PT attribute has the same total, the final centroid value. So any primitive is fine if it's being hit by the find function. Find attribute searching at the second input. You are searching for the cell PT, and you want to use the current point number, the original point number, and cell PT. If it's the same, then it's the primitive is being linked. The cell is being linked to that position. Okay. Okay, I think I'm missing something. I need to specify what kind of type I'm looking at. So I'm looking at the primitive attribute. Alright. This should give you the result. Let's check. If I'm getting more than 0, then that's successful. Okay. If I'm getting negative, then that's something wrong. There's something wrong here. So I think I'm having something wrong here. Let's see. Do I have cell PT? Yes. And it's until 999. That's fine. The number of points is, why do I have this much number here? Because of this out. I'm gonna temporarily connect this here. This should fix it. Now I should have 1,000 point here. Then I have prim, which is always more than 0. Okay, that's good. Now that I have a primitive number, I could get the centroid out of this primitive. What's it called? Centroid, yeah. And just swap the current point position with this centroid. And in case you couldn't find your current point number, if prim is less than 0, then just remove yourself. The point is not being used anymore, so you can just remove it. Which I hope wouldn't happen, but just in case. Okay, so let's see the difference going from this point to this point. So you see some changes happened, and I want to really check if the centroid calculation for this 3D surface is correct. So I'm going to use the measure node again to check. Okay, so for the measure node, I am going to use the centroid, and I need to do it per piece. So in order to do it per piece, gotta use this one, and I'm gonna use cell PT to calculate the centroid per cell. And it's gonna be promoted to primitive. Yeah. So let's check. So for the first centroids, look like this from the measure node. For this one, okay, it's a bit different. Close, but it's a bit different. Not sure why, but there are some measuring error here, I guess. Maybe I'm doing something wrong. Maybe. Okay, what could go wrong? Probably right here. So I was having total final centroid, total area here, adding these. Okay, I shouldn't calculate the centroid here. And after this, I have promoted the piece triangle centroid to this one and total area to this one. Okay, looks correct to me. And want to check the CVT part. Okay, now I know. I'm using the weighted value. I'm referring to some kind of weighted value here. So this has some weighted information, so I need to fix that. So this is coming from here. That's fine, but I might need to have a situation where I don't have any weight information. Like this one. So currently I'm using these gradational value to shift the centroid. So I should give some parameters in order to disable this. Let's say switch, and instead of having the colored value, just gonna give all white value. For each point. Or just derive from the original mesh. Yeah, that'll be better. Okay, so I'm gonna later create some parameter to control whether I want to choose 0 or 1. Okay, if it's 0, there are no weight on the surface, so it should get the same centroid as the measure node, hopefully. So the measure node centroid is like this, and the calculated centroid is like this. Yeah, there are a few errors on this decimals, but pretty much the same, so I guess this is okay. If you need to make sure it's more precise, you could go to the where I'm calculating the centroid and change it to 64-bit to make the result more precise. Not sure if it's gonna change the result, but no, it's pretty much same. But overall it looks okay in terms of precision. It's not too wrong. Okay. And once I did do this, I need to make sure that this also works for the grid. Okay, so if I change this to a grid, the configuration looks a bit different. But let's check. Centroid. Okay, it's the same. Alright, so it's working for the grid as well. Now going back to the 3D surface and see what happens to the result. Okay, if I play it, The calculation is slow, but yeah, I'm getting the result just like I want it. Okay. Again, it's faster to do a scatter node. But that's fine. Now let's try with the weighted version. I'm going to remap, create a more high res. Maybe this is too much. Yeah, something like this. And I don't need the texture for this one, so I'm gonna delete the texture value. Okay, so that it's easy to see the gradation. Now, let's switch this. So this was using attribute map, but it's not related to the UV, so maybe I should use noise instead to test. So this one could also be switched. Either use noise or texture. If I want to use noise, currently it looks like this. Change the scale a little bit. Okay. Create more contrast. Alright, let's go with this. And so there's only 1,000 points, but still it's not that fast. See if it's gonna work. Okay. Not sure if I'm getting the result. That is because, yeah, well, I do have a weight. Can't really say if this is weighted or not. Really hard to see. Maybe I need more points to check. Now this comes to where I need some optimization, because if you have more points, you need more calculation resource. And the Voronoi fracture is just too slow, as you can see here. So I'll show you some way you could use to roughly estimate the Voronoi. Well, in those cases, I'm not sure how the weighted centroid works. Well, but as you can see, this is a bit too slow to see the result. So I'll show you one of the way I could think of to roughly, you get the rough result but speed up the result a little bit. Which might be useful, or I'm not sure. Now the way is to use more like think about how you could implement the Voronoi image using a shader. It's pretty simple. consider this as a kind of a grid. Maybe I could use another remesh node to remesh the geometry with high density. Again, I could remove the texture. Oops. And I want to give each primitive an information whether which cell it belongs to for the Voronoi. So consider this is the initial point for the Voronoi. Let's try to see which primitive belongs to which Voronoi cell in shader way. You just need to, the Voronoi is pretty simple algorithm. If you have something like that, if you have a center of cell like these, you are always getting the wall here in between these 2 points, and the distance is always the same for this one and this one. Same for these. Same for these. I mean, not the straight distance, but perpendicular distance, I think. Yeah. Or is it the straight distance? Forgot. Yeah, it's the straight distance. No? Maybe not. Anyway, the perpendicular distance from the wall to the point and perpendicular distance from this point to the wall is always the same for each Voronoi. So consider that you could simulate that situations per primitive, whether it belongs to the cell point 1 or cell point 2 also, by just calculating the distance. So connect the remesh geometry to the first input, connect the cell point, center point to the second input, then first get the nearest point for each primitive. Get the point position, or actually you could just use this NPT. You could just copy this NPT as a cell point attribute for each primitive. Okay, and if you color these attribute random from attribute, looks like this. It's pretty similar to what you get out of the Voronoi. You just have some glitches on the border, but more or less you get Voronoi like shape. And if you get the result of the Voronoi, you get similar result. As you can see, it's take a lot of time to calculate Voronoi here, but just copying the color is pretty fast. So what if I could get the centroid, the rough centroid out of this geometry? That will be much faster. Okay, so instead of using Voronoi fracture, I might be able to use these to calculate the centroid. Okay, now since this one is everything triangle, so if I just get all the centroid for the triangle and add all these and calculate the average, you get the normal centroid really fast. In this case, you could actually, if it's just a triangle, you could get the centroid as at P for the triangle. Simple as that. You don't really need to access the point numbers. Well, if you are going to deal with the weight, maybe you do, but you just need a normal centroid. This will just do it. And then after getting the piece triangle centroid here, what you want to do now is to get the average out of all the triangle centroid, just like you did to calculate the polygon centroid. So you could use attribute promote or the primitive, get the average of piece triangle centroid, change it to centroid, and per cell PT. And if you look at it, you get these values. And let's see if this is decent or decent enough by moving this initial point position to the new centroid by using similar things that I did here. Just gonna copy this here. So I want to move the original points, yeah, referring to the second input, which has the cell PT, and move the point to the new centroid from here to here. Okay. And if you and that looks a bit more distributed than previous frame, so let's see if this setup is useful inside a solver to see if we can calculate similar result like we used for the Voronoi. So I am going to connect the remesh geometry to the fourth input. I'm going to copy this one, which has to be done iteratively. Paste it somewhere. This is really slow. And for the primitive wrangle, I'm going to connect the fourth input here. Then recreate the color. Recreate the cell point number here. Attribute promote to average the centroid, and update the original point position to the centroid and see what happens. The things you want to check is the speed here and the precision. See, if I play it, you can see this is much faster, and the result is not too bad based on the resolution. If you increase the resolution of this mesh, you could further get more precise, or if you make the mesh more rough, you get faster result, less precision. So if you just need a simple animation or a rough result, then I think this is the way to go. Instead of using normal Voronoi structure, you could use kind of a shader-based Voronoi calculation like this one. Now, when it comes to the weighted value, here's things that I never tried. So let's see if I could do it on live. Okay. Now, first of all, let's give an option to switch between the normal fractured version and the shader version. Okay, so for the weight information comes from here. So I gotta use this one in some way. Let's make this organized a little bit. Let's call this fracture version, and this is the I don't know, pixelized version, maybe. Okay. Now, in order to use the weight, you need to shift the centroid of the triangles based on the weight. So to do that, how I be able to do that? I mean, previously I was getting the weight for each points on the triangles to see in which direction I should move, but I think that's gonna be really slow because I have so many triangles here, so the movement will become really slow if you do this way. So instead, what I'm thinking is to use, well, I just gotta try if that's gonna work, but first thing I could think of is to calculate the gradient of the CD and use that gradient to move the point to that direction. But the problem with this method is that it's not gonna stop, so maybe it's not a good idea after all. But let's check. If I calculate the gradient for the CD, you get how the point should move. Yeah, maybe this is not a good idea. Okay, after all, maybe I should just think about how I could shift the centroid based on the weight. Now, how I was doing it. Let's see. So looking at this one, oh, can you hear me? Let me raise up the volume. Can you let me know if you can hear my voice? How much works you got in your math in your 12th standard? Not sure. Well, since the way you measure the score in Japan is a bit different, so not really sure. Okay, where was I? So, so previously I was calculating the weight like these. Probably I should use the different way. Sampling is fine. No, the problem is how I should use this. Okay. Okay, I think I have some ideas here. Just like I'm doing here, I actually can think the cell as the bunch of triangles made up with bunch of triangles. So if you coloralizing it based on the cell PT again, okay, am I missing? Okay, so for each cell you have triangles, and you can calculate the centroid for each triangle just by getting at P, and you can multiply weight to each of the centroid and then add all these weighted point position and then divide it by the total amount of weight, and that will give you the result, I guess. Yeah, that's the way to go, I guess. That should do it. So it's not really a pixel, but I'll just call it pixel because initially it's for the grid based images, but you could also use for the meshes as well. So what I'm going to refer to is this weighted surface. Yup, and for each point position I can calculate the weight by UV sample. And using current centroid of the triangle to sample. Okay, now I could multiply the current centroid of the triangle with the weight and place it in this attribute. Now now I cannot really use average anymore because this is just dividing with the total number of primitives. So instead I should divide it by the total number of what was it? Total number of weight. Yeah, that's it. So I also need to have a total number of weight. Piece weight is equal to just weight. Okay, so instead of using average, I'm just gonna keep it right here. Promote for each cell PT I'm gonna calculate the sum, the total sum of piece weight. That was the name, right? Yeah. Change the name to total weight. Then finally divide the piece triangle centroid, the sum of the piece triangle centroid with the total weight. So I should have another promote. In this case, I should add all the triangle centroid and total triangle, centroid per cell. Yep. Now finally I'm gonna calculate the final centroid by getting the total triangle centroid divided by total weight. Okay. And if I'm getting the result for this one, when I don't have any weight on the surface, let's switch this to 0 so that everything is white. The weight is all 1. And if I'm getting the same result for the centroid for this one and this one, then I'm using the correct method. So let's check the centroid. Looks like this. And if I look at the measure node, okay, is it the same? Yeah, I think I'm getting the same value here. So that looks good. That looks good. So I think this is working. Connect this to the second input instead. Just disable this. And switch is equal to 1. This is just remapping. Okay, let's see. So this is without the weight. Let's see the result. Yep. Good. Now let's have it with the weight. See what happens. With this speed, it's easy to check whether I'm doing correct or not. Not really sure. Maybe let's make more contrast to the surface. It's a bit hard to see what's going on here. Okay, so I should add additional clump or fit function here. Fit the current CD with clump minimum clump maximum. 0 and 1. Okay. And where is it? Okay, this gives you more higher contrast. Okay, let's check with these. Save it, play it. Okay, so maybe I'm not getting what I really want here. This looks pretty even, so maybe I'm doing something wrong here. So this is the weighted mesh. This is coming from here. Yep. And I'm hopefully getting the weight here. Well, let's check if I'm getting the correct weight or not. Okay, so I am having different values here, so it looks good. Okay. And piece weight, I have it here. Piece triangle centroid, I have it here. Right. That looks okay. Now, if I look at the attribute promote, I should be promoting total triangle centroid and piece weight. These value has to be different for each cell, so let's see. Triangle centroid looks okay, total weight. Okay, so this has different result as well. Okay. So this is getting some value here. And finally the total centroid is based on here. Let's compare with the original centroid and final centroid if these values are different. If it's different, then that's good. If it's not, something must be wrong. Okay, so centroid here. Okay, so it is different. No, yeah, it is different, so should be okay. Maybe it's just. And finally remapping. So I'm gonna make sure if I'm referring to the correct value. Yeah, looks correct. Just the result doesn't really look. Maybe I should make a Voronoi to really check this is. Just using weight to distribute. So I'm going to use the final result to recreate the Voronoi cell. To me it looks like it's evenly distributed. Let's check with the grid, which should be much simpler to check. Okay, the grid might be too big. Okay, let's check with these. Check the weight. Okay. Let's see what happens. It's not really doing what I want. And as you can see, the precision is not really good. Probably due to the resolution of the Voronoi cell itself. Yeah. Maybe I should make the original remesh geometry a bit more high res to have more crisp edge to get better result. But if you do that, you get slower result. But still it's faster than the fractured version. And I do see some gradient here, so let's see if it's in some here. If it's related. Yeah, it's kind of related, I guess. So I guess it is working. Let's try with the image. Let's see. Yeah, it is kind of working. Yeah, that's cool. Good to know. And the good thing about this method is that you could increase the point number a lot to calculate, because every point's being calculated multi what was I trying to say? Multi-threaded, so it's pretty fast. But if you have more points, you might need more resolutions for the sampling mesh. As you can see, this becomes a low, like this one is pretty low res. So and if you increase more of this mesh number, then you get slower results. So you gotta find a good result, I mean balance between them. Anyway, that's how we could do it. Okay, looking good. Now let me try to organize this a little bit with all the parameters. It's getting a bit messy here, so I'm gonna delete things that I don't need. And as always, I am going to, what's this? What was this? Oh yeah. This is, yeah, this was just the testing, which is stored inside Voronoi, so but maybe keeping this as a final test result is good. So wait, I don't really need this actually. I could just use this, and I could delete these. Okay. Okay, so this is the main solver. This is for the weight. This is for the pixelized sample. And this is the initial point. Okay, and this is the input mesh. Now, let's add a controller. So that I can control unimportant values like the number of points and so on. Okay, first, number of points. Voronoi cell number. This is for the pixelization. So to use that, you need a switch between the fractured version or not. So let's make this name fracture version. Okay, this is true or false. Copy this parameter and change this, use this, where should I use it? Inside the loop here. So if it's equal to 1, I want to use fractured, so I'm going to replace this here. Like this. So if it's equal to 0, it's gonna use the kind of a fragmented shader like stuff. If it's equal to 1, you're gonna use more precise version but slower. Alright. Slow and precise. Okay. And for this one, whether you want to use weight or not. Which could go here. If it's equal to 0, you just have a single color weight. Okay, for this one, what was this? So this is to use either texture or noise. Okay. Maybe I should use a ordered menu for that. Call this weight type. The menu here. The first one is noise. The second one is texture. Okay. And I only want to show this when this is turned on. So maybe I could use a parameter like hide when. When use surface weight is equal to 0, hide it. Okay. Okay, makes sense. Now, what else? Okay, I didn't copy that value. Copy this here. Okay. And this switch is, I mean, based on your input, it's just gonna change, so I'm just gonna leave it here. Or maybe I could give a slider in terms of shape. Which shape you want to use. Now this is all for surface-based geometry, so if you want to do it for volume, then you gotta re-update the value again somehow. But again, you could use real volume information like this one instead of the pixelized information for simple Voronoi value. Well, the problem is that you cannot use attribute promote for the volume, so maybe you gotta think about some other way. Maybe. Yeah. Or you could just use the grid points instead. I'll leave it to you. Okay, what else? Let's also have the final result with the fractured information. So for the fractured value, you want to connect this one here. You don't want to calculate the interior surface. Promote the cell PT and colorize based on the PT as well. Let's check with the 3D mesh. Okay, I think I'm using the remesh value a little bit too high for this 3D. So this is the fractured version. This is the pixelized version. Yeah, this is a bit too high qual. Maybe I should also have the parameter for this one. So let's start with really small, really big number, this one. Now obviously this is really low res, so the result will become really low as well. If you look at it, well, if it's 3D, it's a bit hard to see. If I make it grid, yeah, there are a lot of like unstable point position here. That is because of the precision of the Voronoi cell. If I don't use the surface weight, yeah. So let's have the parameter, this one. If I'm using the pixelized, I should show this parameter. Range 0 to 1 is fine, and hide it when the fracture version is equal to 1. So all right. So okay, and if I make it 0.01, you see that the result becomes a bit better. If I make it 0.005, the remeshing part takes a bit of time for initialization, but the result will get better. And the speed is not that bad. Yeah. Okay. And if you change this to a fractured version, you don't really need these parameters, so it's gonna be hidden. Okay, makes sense. I think that's probably much it. Yeah. Yeah. Maybe subdivide the remesh to increase the res. Oh yeah, that makes more clean result, I guess. Maybe instead of remesh. Shall we try that? Shall we try that? Let's try with the pig head. And as a result, it's better to have a triangle. So let's use open subdiv loop. Yeah. second depths. Let's see what happens if I replace this one. Interesting. Maybe the quality here isn't that good, but let's see what happens. Okay, maybe the subdivision is too high to calculate. Or am I using the pixelized version? Nope, actually not. Just change to the pixelized version. Okay, the result is fast, but how precise is this? I don't know. Interesting. It is interesting to see the result. Maybe I could subdivide a little bit more. The speed is still decent. Pretty nice. Can we have a weight? Noise, yeah. Not sure if this is changing anything. Maybe I should increase the scale a little bit more. Like that. This is more obvious. Okay, now I see. Nice. Okay, so using subdivide maybe makes more sense than remesh because it's also faster to make high-res geometry. Interesting. All right. Nah, good. That looks good. Interesting animation. And so on. If you check with the Voronoi, fractured Voronoi, the shape is pretty much the same, you just get a nice edge. But with slower computation. Okay, I think that's about it for today. I think I've done enough for today. Well, thanks for watching. Maybe I should also have an option to switch between the remesh and subdivide. I'll make one more parameters and finish this live. Let me know if you are still here and have any questions. If not, I'm just gonna end as soon as I've finished organizing this. Well, as always, I am going to upload the file and paste the link to the video description page of this video so that you can download it. You can use it for free for any usage for your. But as I said in the first place of the video, if you just want the final result, then just use the scatter node. That's much faster. So if you need animation like this, maybe this makes useful. But this is only for educational purpose, so which I learned through my process, so I wanted to share with you. I'll have another ordered menu to choose whether I want to use the remesh or subdivide for the pixelized mesh. So okay. Now this one pixelized meshing should be hidden when fracture version is on, so use this one to hide. Oops, it's gone. Now this one also should be hidden when you have chosen the subdivide, and instead you want to show the subdivide level. So if fracture version is 1 or where is the okay, or pixel meshing type equal to, what was the value? So if it's equal to 0, you want to hide it. So instead you want to show the subdivide level, which is an integer. So let's bring this here and use the similar, just change it to 1. Okay. Now let's check. Wait a minute, it's not being hidden. Maybe I'm doing something wrong here. Maybe the OR condition is not being written correctly. The condition, the way I have to write the condition is very unique, so maybe I gotta search for it. Well, this is written in Japanese. Okay, so if I write it like this, this means or. Seems like so. Okay. this is obviously something wrong here. What the? Okay. Division level. Okay, let's see. So subdivide, remesh, okay, it's changing. Okay, cool. Let's just start with 1. Okay, everything is tied up. That's it. Thank you very much for watching. This is it for today. Hopefully you liked it. We'll try to do the live stream more constantly. I've been a bit busy these days, but hopefully I'll be able to find some time to do more. And maybe with another topic like Python as well, since I'm using a lot these days. So yeah, that's it for today. Thank you very much. As always, if you would like to download the files, you could download for the video description, and if you would like to support me on those kind of tutorial, there's a Patreon, so it would be great if you could also support me there. Okay, that's it. Thank you and good night. See you soon.